hopefully.
Yeah. Using custom setting. Okay, I think we're good now. Yeah, so as I was saying, modes of operation and concept of operations is big fancy terminology for what the satellite has to do to actually be a satellite. And so what I've shown in the past is this image here, which is what the CSDC, or what the organization that hosts the challenge, provides us. So they've broken it down into 6 steps. And what I'm hoping to do is just go through these 6 steps and then show off kind of what we've done over the summer and give like a really big outline of all the implementation strategy for these 6 different steps. So at its core, what the CSDC mission is the selfie sat, and to be a selfie sat has to perform these 6 things. So the first thing, as seen here between the amateur radio operator and mission control, is that once the selfie sat has been commissioned and is ready for nominal operations, an amateur radio operator from around the world will contact the mission control center in order to request a selfie sat pass. The ARO, or amateur radio operator, will send mission control the location specified as latitude and longitude of the center point of the desired space selfie image. So that's done in the first step. And then in the second step, the mission control center will reply to the amateur radio operator with information about the selfie sat pass regarding the start and end times and a password that the amateur radio operator will use for the pass. And so that is just communication between amateur radio operator and mission control. In step 3, the mission control will uplink the pass time and the required roll angle for the selfie sat to be able to point the camera bore sight at the ARO's, or amateur radio operators, specified location during the pass. And so, as they're saying, that the latitude and longitude maps to the exact middle of the image. And so then, as the selfie sat is flying through its orbit, it will eventually pass over the amateur radio operator and enter into step 4, which is during the pass, the ARO will contact the selfie sat directly and will uplink the command to acquire an image when selfie sat is over the desired imaging area. Only one image will be acquired during a space selfie pass. Then, as soon as the command is uplinked, the selfie sat will immediately take the space selfie photo with the selfie cam payload imager. So that's seen with this fun little graphic. And then the selfie sat will then immediately begin to downlink the space selfie photo to the amateur radio operator. And during a pass, a selfie sat may also downlink other information, such as a list of recent downlinks or other material determined by the CSDC. So again, that's what the CSDC gave us in the rules and regulations. And then they said, go wild, build a system that implements this. And so there's a couple interesting things to note just from these 6 steps. Big area of concern is there's not just communication with us and the satellite, but there's also communication between us kind of acting as mission control to other amateur radio operators. And then there's also communication between amateur radio operators and the satellite. So there's a lot going on and a lot of opportunity for other people to contact the satellite, because the amateur radio operators can be theoretically anyone in the world. And so that's now just very specific to kind of the pass. A couple of other things that we can highlight are in the first step, noticing that it says once the selfie sat has been commissioned and is ready for nominal operations. So that means there's a phase between when the selfie sat gets launched and between it's ready for nominal operations. So we'll look at that a little bit right now. And then because the selfie-sat may or may not be contacted all the time, there's typically space that the selfie-sat is just kind of in orbit. So we have to figure out what else is it doing in orbit. And then, of course, how does the selfie-sat know when it's in the pass area, and then handle all of these different events that can be happening. So what that kind of looks like in the large kind of system overview is a concept that's called modes of operation. And so what the modes of operation are like very big, large scale like functionality of the satellite that kind of governs a lot of different areas of what the satellite can or cannot do in that given mode. And so the first mode kind of alludes to the idea that I mentioned before, when there's a period between launching and nominal operations. And this is called launch in early orbit phase. And then it brings us to what we're going to call our default mode. And then from default, there's 3 areas in which the satellite can enter into. The first one is safe hold, the second one is survival, and the third one is pass. Now, what the CSDC mission kind of describes is a little bit of default and a little bit of pass. What we've introduced kind of internally is what we're calling safe hold and survival. And these modes are kind of like protection modes, in which if anything were to go wrong in the satellite, it kind of defaults to these modes and like turns off a few things. So I'll pause there. Does anyone have any questions, comments, concerns about these 6 steps or like the large modes of operation with the system overview? Does that kind of make sense for everybody? Seeing some nods, so that's okay. And you'll see it is a little chaotic. I've tried to do my best to kind of tidy it up, but if any software people or just, I guess anyone who's kind of interested in system design, this kind of mirrors what's called a finite state machine. And so you can think of that as there's different states. In this case, we're calling them modes. And then in any given state, you're allowed to only go to a specific other state given a condition. And so what we're calling these are exits. So you're in a mode and then you're allowed to exit that mode under a given situation. And so we've listed some of the exits surrounded here and then provided the location in which the exit will take you to. One really interesting thing to note is that from default, you can go to any one of the modes except the launch and early orbit phase, because you never really need to go back to that. But to get to pass, you always need to start in default. You can never go into like a survival or your safe hold mode and go straight into pass. And the justification for that is you want to deal with the critical issue first, then do your nominal operations. So that's large system overview. And we can go now deeper into each one of these large scale modes and see what kind of we can break apart with that. So starting with the first one, oh no. There we go. So each mode is what we're separating into different events and different tasks. So each mode implements a task or a bunch of tasks that will be controlled with software and hardware. And so this is the launch and early orbit phase. I'm calling it level 1 mode. It's just kind of an arbitrary thing I've decided. And it starts right from the release from the P-pod. And what the P-pod is the deployer mechanism that separates the satellite from the launch vehicle or the rocket. So release from P-pod, the satellite must know that it has been now released from P-pod. And so the way we've implemented that and the way it's required to implement it is what's called limit switches. So there's switches on the back of the satellite that get decompressed or compressed when they're in the satellite and then decompressed when they leave the satellite. So that's one way to tell. Then we slowly go into all the different tasks that get the satellite ready for nominal operations. So these include power, deployment, and desaturation are the biggest ones. Or not desaturation, detumbling, sorry. So we first focus on enabling power generation. So that's handled by EPS and OBC. And your exit for that is your battery is at some threshold, in which then you can enable and start slowly turning on all the other systems. And that's included in the system starts. Sorry, I should also mention that each one of these tasks has an ID associated with it. And then, of course, each one of the tasks also has an exit associated with it as well. So we've launched our satellite from the deployer. We've enabled power generation. We're getting energy from the solar panels. We're slowly turning on our systems, but then we also have to recognize once we turn on systems, that's when things can go wrong. And so what we're doing is you first have to realize that if something is to go wrong, you first have to detect that something went wrong, and then you have to respond to the thing that went wrong. And so we're calling these the things that go wrong faults. And when you enable faults, you're enabling the detection of these faults or enabling the detection of something that goes wrong. And typically something that goes wrong is there's too much power, too much heat, or your voltage is too low or too high as well. So we first then test for, or we enable faults. And by enabling faults, we're now allowed to go into our safe hold mode and our survival mode. And we'll look at those in a little bit. So then our systems are on, we've enabled faults, but from the deployer, our angular velocity is crazy. I think it's like upwards of 35 meters per second. It's just rotating crazy fast. So what we have to do and what ADCS is in charge of is slowing down our satellite to a controllable angular velocity. And so once it does that, we can then receive ground communication because we can now not orientate ourselves, but we are in slow enough angular velocity in which a small signal can now reach our satellite. And that's handled by the ground reception orientation. So then moving on, this is a communication task. And so once we're slow enough, operators on the ground want to know the current state. And so we're going to transmit some telemetry information to kind of provide users on the ground and mission control where we're at in our modes. Then, however, our communication throughput isn't at its most optimal, especially if we want to downlink an image. So we have these deployment commands. And the reason why we need to implement deployments, there's a few reasons. Sorry. Is that primarily for our antennas, their length exceeds that of the CubeSat longest dimension. So we have to compact them inside so they fit into the deployer. But then, of course, we want them fully extended for maximum throughput. So we have to deploy them. And so we implement an antenna deployment system. And then these are the two steps to actually implement that deployment. And so as a requirement from the CSDC, we have to break this deployment into two steps. They're calling it arm and fire. So you can kind of think of like arming your gun and then pulling the trigger. So it's separated into two commands. Then once those commands are implemented, we need to be able to detect if they're implemented. A lot of the software and hardware is you can think of as perform a function and then know that you performed the function. It's because it's in space, because it's 600 kilometers away, because you can't actually see it, you really need to think like, how can I make sure that every single thing I'm doing can be tested? And so that's where a lot of like the faults come in. That's where a lot of like tech deployment comes in. So again, we move on. We've successfully deployed our antennas, and then we want to transmit that again. And then comms can do some data throughput analysis and do some specs with that. Then, since that took up a lot of power, we want ADCS to point us towards the sun and then enable power generation, and now we can move on to our default. And so now our antennas are out, all our systems are on, we're powered up, we're relatively good to go. And then I won't spend too much time on the notes section here. This is a lot of just reference to what the CSDC gives us and why some of these tasks are implemented, and reference the requirements. And so I guess right there, I'll pause again. Does anyone have any questions, comments, concerns about the launch and early orbit phase? Yeah.
I've got one question about the second phase there, stable power generation.
Okay.
So actually, a couple questions. One, are we going up with dead batteries or half charge batteries?
So that's a great question. The time between the satellite getting put into its deployer and it actually launching can be upwards of 6 months to a year. So yes, we can charge our batteries and we can hope there's a little bit of charge, but yes, they might be dead by the time it's launched. Yes. Yeah.
And this is all happening, it's going to be charging while it's still expecting to spin, right? But I suppose there's nothing you can really do about it.
Yes, exactly. Yeah, it'll be all passive charging. Yeah. Yeah. Cool. Yeah.
In what stage will the OBC be before all the systems start? Because you said it can be like months.
Great question. Yeah, that's something we need to figure out. And then we can like look at the fine details of that. But what I would say is we define like a boot up sequence and like an initialization sequence. And I would say for all systems, we would need to define a boot up sequence and an initialization sequence. And then maybe it would be like OBC sends like a handshake signal out to all the different boards to see like if it can communicate to each one. Yeah.
So it should be triggered by EPS probably.
Yeah, as soon as it's powered on. Yeah. Yes. Yeah. Yeah. And then OBC, it's a really interesting subsystem because as you can see, like there's a little legend off to the corner here, and each one of the tasks are associated with a subsystem more or less. But OBC is also has to kind of take a step back and are the subsystem kind of implementing the entire flow of this as well. So yes, OBC has dedicated tasks that they have to do, all these blue ones, but they're also in charge of the detection, the faults, and making sure all of these kind of things happen when they need to happen. Yeah. Stephen, yeah.
What happens if that limit switch gets pressed? Will we go back into this mode, or will it ignore it, or will we go into
So the P-pod is attached to the rocket. It has springs in it, and then once the rocket, like the systems on the rocket, opens up the door on the P-pod, we're now in free space. Oh, and there's like, are you saying there's like could be a little bit of jitter back and forth?
Like if you have a case where this very slightly or something like that, but not just to visualize space,
I would say the vibrations of your rocket launch are quite high. And so the period of time between your system turning on then off again, very little can happen and would be out of our scope. CubeSats, we're not, yeah, so I guess I should also mention that. Yes, we're a satellite team, but we're also building a CubeSat. And so CubeSats are a little special. They are meant mostly for very quick, very like demonstrative payloads. And they have a huge design philosophy of keeping it simple. The design should be simple. It should do kind of one thing. And if it doesn't do that, it'll get it on the next pass. So keep the design simple. And that's just like a philosophy you should take it for all the different subsystems, all the different projects. Keep it simple, do it well.
A question like you're talking about, you try and perform an action and then you always have to check whether or not that's succeeded.
Yeah.
If that's a software action, that's fine. You fail and then you try it again. But deploying comms is more of a mechanical thing. So how, if you fail a mechanical operation, can you do it again? I mean, are the resources that are spent doing that that we can't recover?
Yeah, that's a really good question. The biggest mechanical like task that you would need to do is the antenna deployment. And there's a couple things that I would then ask, like, in what areas would that not work? So did the melt or the trip wire did not melt, or did an antenna arm break? And so I would then say, like, okay, how do you detect if it's melted? How do you detect that it's broken? And yes, you could end up launching a rock in space. CubeSats have done that in the past. It's unfortunate, but you then downlink as much as you can, and then on your next CubeSat, you'd be like, okay, we're not doing that design again. We've learned from our mistake. So yeah, so kind of a shitty answer, but you have to learn from your mistakes. Yeah. Cool. Does everyone mind if I move on to the next default mode? Cool. So I know this is quite a bit to see. I might be able to do something like this. Cool. So you can basically think of the satellite as just a big loop of different events that it wants to be able to control. And so the first question is always, do you have an event planned up? And so we have multiple events that are just identified and just going to be loaded onto the satellite. And so the first event is a power event. We have an ACDS event, a calibration event, a secondary payload event, which is questionable, and then we also have a pass event. And so each one of these events can be expanded on more, but by default, what the satellite's going to be doing is it's going to have like a default schedule. And in that schedule, it's going to have power, ACDS, and calibration, and maybe a secondary payload if we want to do that. And it's just going to do those in loops. It's going to check if what our battery's at, and if the battery's too low, we're going to load into a power event, and it's going to implement that. If our reaction wheels are saturated and we need to dump some momentum, we're going to try to desaturate the reaction wheels and then try to reorientate ourselves best for an upcoming communication. Then we also have a calibration event because we are dealing with an Earth observation payload or a camera. Your camera needs to be calibrated for different conditions. And so that's what this task or this event kind of covers. Then, of course, we do have space for a secondary payload. So I just kind of threw that in there. It's kind of just a placeholder for now. And so by default, it does these 4 events, and we'll only go into a pass event if it has one of those communications that the mission control gave us as an amateur radio operator contacted them. And if there's no event, we're going to see if we've received anything from communications, execute any commands that are immediate or immediately tagged, and then load in the schedule that the mission control gives us, or provide that default schedule of power ACDS calibration secondary payload. And so this is like the main control loop that we all collect telemetry and transmit telemetry as well. And so it just keeps on going through this main loop. What we're kind of interested in, where the selfie-sat gets its namesake, is when a pass event occurs and we have that required roll angle, we have the location, and we have that pass time. And so what that looks like is ADCS points to the required angle to have the camera's bore sight or its direct line of sight point to the direct center of the image. Then OBC checks to see if it has enough memory. And then if not, it can implement different strategies of either getting rid of old memory or just saying, no, we're not going to take the picture, we can't. Goes into a system health check. And then back to what we were talking about with fault enabling and fault responses. Up until this point, we're doing everything we can to say we're good. We've got good battery state of charge. Our camera's looking good. Our angular velocity is all good. We're doing as much as we can to prevent faults from happening when we go into the actual taking of the image. So once we want to take the image, we disable our responses to the faults. And then this is now we're actually like implementing the different steps involved in the what's given by the CSDC. So we get a handshake signal from the amateur radio operator. They provide the password that we then have to authenticate. And then because this can happen as soon as the satellite comes over the horizon, the satellite is probably going to want to wait until it's directly overhead the specified location, and it's going to do that and wait until it receives the amateur radio selfie command. And while it's kind of waiting for that command, it's going to do its image parameters and using all the calibration data to set the image parameters. Then it does the big flashy image capturing. It compresses the image and transmits that image to the user. And then again, I don't know why there's a 1 there. It then enables the fault responses. So if anything goes wrong here, we can now respond to it and act on it, and then go into our next events. Okay, so that was level 2 mode, the default mode, which is this big loop, and then the pass mode, which was implemented lower down here. And then again, there's a note section if you guys want to read this, where it just provides additional explanation, justification, and relates back to the CSDC requirements. Does anyone have any questions on default and pass modes? Yeah.
Is there any way of establishing priority over some of these events? So like,
yeah,
for example, if, I don't know, the reaction wheels are saturated, but there's also a request for a pass.
Yeah.
Is there a way of distinguishing that? Is that an OBC problem? Is that subsystem problem to let OBC know that there's like a fault that it can't do a certain operation?
Yes. I would say that's kind of covered in like system health check. The implementation of that is still up for debate, but yeah, it could be exactly that. It could be like collect all telemetry, parse the telemetry, and if there's certain conditions that are happening on like ADCS being too saturated, then it'll go back to its like main loop and just won't even go into the camera. Yeah. or pass mode, sorry. Yeah. Yeah. So I would say step 3, mission control will uplink the pass time and roll angle to the selfie set. That like describes the location for the pass. And then that kind of gets implemented in here, load new schedule. So that is mission control providing that pass information in a schedule that would then just be labeled as an event. And so as if we know location and or time, we can then go into that pass mode event. That makes sense?
Yeah, but then
Step 4. During the pass, the ARO will contact SelfieSat directly and will uplink the command to acquire an image when SelfieSat is over the desired imaging area. That to me is like the amateur, the SelfieSat can pass over the location, but if it doesn't have contact with the ARO, it's not going to do anything. It's kind of like the amateur radio operator like pressing the shutter button on a camera and like taking that selfie. So there is still implementation for that. Yeah.
What do you mean by no faults detected? Because like I feel like the whole purpose of it is like of the satellite is to take a picture, right? Like let's say we have like a small problem with like I don't know, memory isn't being uploaded to an SD card, but we can still take a picture and still like communicate information. Like should we like continuously keep trying to fix it, or like when do we say like okay, like we can't fix this anymore, like we can just say uh like let's just take the picture and like just sort of accept that we can't save data anymore.
I would say as long as you can get it to the end user, then you can kind of separate that between like, that's why we have like safe hold mode and survival mode. Survival mode is like, don't do anything. We got to focus on just keeping ourselves together. Safe hold mode is more like, we can still do some functionality, but we might not be doing it well, or some other functionality might be limited or just off.
Okay. And I think we should for like safe hold and survival mode, I think we should definitely have like almost like a stress test sort of day where like we just sort of say like, oh, what if we just remove like this wire or this wire? Like what if we move like the clock interface, or like what if we remove like the I2C data line? Like can it still operate? If it doesn't operate, can we find a solution to see if it can operate?
Yeah, that's a wonderful idea. Yeah, I think we should all like, or if we have time, like write test plans for our systems, and then testing out like that full subsystem. And if something goes wrong with one of them, how does that impact the greater system? Yeah, it's a wonderful idea.
Yeah, and I think it should be like a sort of like an open sort of fun thing, because like sort of fault testing is more about creativity than anything else. Like the more ideas we have about how we can sort of destroy our system, the better, because we have more like coverage in that sense.
Yeah, definitely. That's cool. Okay. Cool. Actually, well, speaking of the next two modes, looking at safe hold and then going into survival.
Oh, sorry to interrupt, but you stopped sharing your screen.
Oh.
You're good. Yep.
Cool. So again, we, just like our events, we start with is a fault found, and then again, this is of course implemented by OBC in enabling, disabling, and detecting various faults. And so if we found a fault, let's just focus on that fault. So we disable the fault test because we don't want to be trying to work on something and then constantly try to like go back to this fault found and get stuck in that loop. So you want to disable that and then try to focus on that or remedying that fault. So we do that, then we disable the payload power. We want to protect the payload at all costs, and if we're debugging and turning things on and off, just disable the payload for a moment, and so it's protected. And then we have fault testing, but then we also have fault responses. So we can detect a fault, but kind of like as Harrison alluded to, we might say, yeah, but it's no big deal. We don't want to respond to it. And so for each fault, you can have it mapped to an enable and disable state, and then also enable and disable response to it. So what's interesting, if it's yes, there's about 4 different safe hold faults that I've identified, but of course we can add more to it. So the first one is an EPS fault. So it's looking at the battery state of charge, and it's typically if the battery is running too low. ADCS is going to point us to the sun if they can, and then focus on maximum power generation so we can bring back our battery. Another one is another EPS fault. So it's our overcurrent. So we're gonna do a telemetry request on all the different systems and make sure, set the system off, make sure that it's off, and compare the expected state with the actual state and make sure that it's off, and do the same thing and just turn it on again. Usually if it's an overcurrent, it's something to do with like an event latch up, and a really good remedy for that is simply power cycling it. The third fault is ADCS fault. So there's a sensor failure, and so that we're going to disable the reaction wheel desaturation. I don't know if that actually makes sense, but we'll work on that, I guess. And sorry.
I think a more likely fault would be actuator faults.
Okay.
We can expand ADCS fault to both actuator and then if the mitigation is, I don't think actually be able to separate.
Nope. I think that was just copy and pasted from something else. So yeah, definitely. Cool. And then there's also like an OBC fault. So a single event upset or a bit flip. Another mitigation, or not mitigation, but a way to get rid of a bit flip is typically just to turn off and on a system again. So we do that reliably, turning it off and on. And then since we disabled the fault test, this is us now handling the fault, and now we want to enable the fault test again to basically verify if what we just did caused a solution to it. And then of course we want to transmit, or at least packet some telemetry. So when we pass over mission control can see like, okay, these faults just all occurred. How many are occurring? At what frequency are they occurring? And how bad are they? So that's safe hold. Survival is very, very similar. But it's kind of what Harrison alluded to with your different like thresholds and the different severities of each of the faults. And then again, we don't just disable payload, but we also disable some other components. What those are, I'm not too sure yet. And what other features we need to disable, I'm not sure yet, but that's something we can figure out. But again, it's like a greater state of charge. It's another overcurrent. It could be actuator, maybe sensor failures one, actuator failures another, single event latch up, and then over temperature as well. And so again, for each one of these faults, we first disable the test because we know we have a fault. We do the mitigation or the solution to the fault, a response to it, and then once it's done, we enable it again. and then we go back to just detecting faults. Last but not least, we have mission control. And so mission control, that's kind of us. So we collect amateur radio operator requests, what that looks like, whether that's just them emailing or talking to us or whatever, that's still up for to be determined. But once we have information and communication from the ARO, we generate the roll angle and for the pass, we generate a password for the pass. We calculate the power generation. If it's a very large roll angle and we need to sustain that for a while, it's going to require a lot of power for reaction wheels. So we need to also include that for the event description. And then it's going to create a master schedule for all these different passes. It's going to then try to communicate with the selfie-sat, receive information from the selfie-sat, so any telemetry, all the data that we've been talking about, and any payload images. And if it's good, then we uplink that master schedule. And if it's not, that's when we start being able to control and assess the situation on board the satellite. So if we're noticing that there's a system that's constantly being power cycled and our systems are no longer working, we're going to try to send up some debug commands and some tasks that the satellite can execute to hopefully remedy the error that's happening. And so what this is, or where this is implemented on the satellite is, is here. And the execute or receive mission control commands, execute those debug commands or anything else, and then load in that new schedule. So we've talked about what the satellite does when it gets into a pass. We've talked about what the satellite does just by default. We've talked about a little bit about what mission control does. And I just want to now briefly talk about kind of how that gets implemented in software. The way I see it is kind of what I don't know if this is the right word, but kind of like a software architecture in which we start with like a satellite class, and that class is able to have all the different modes that we talked about. So default, pass, safe hold, and survival, and it's able to switch between different modes. Then in each mode, we saw that there's different events. There's the power events, the ADCS events, there's the pass events. And so then each event has different tasks that get implemented or to like provide the functionality of the event. And so the scheduling and handling of these events and of these tasks are what I'm calling, or what I hope we can implement as managers. So we're going to have a task manager, we'll have a fault manager, we'll have a power manager. So all these managers kind of oversee the timing and the execution of each task. Then each task implements various functions, and then each function, or all these different functions, should be grouped together in libraries, and so that each library can be kind of shared amongst the team. And then, of course, each function, or the groups of function, will have drivers in which it'll actually communicate to the hardware. And then, kind of on top of all of that, we have what's called description files. So that's what we provide from the mission control to the satellite to describe a pass event, to describe the power events and all that. And then we also have configuration files. Because we're changing our systems, because we want to be flexible, because we want to be reusable, the best way to do that is having a set configuration file that represents your hardware in software, so that any function can read the config file and then implement your driver. And so you're not hard coding GPIO names, you are reading a config file. So if you want to test, if you want to change things up, you only have to change the config file. You don't have to do anything in the actual functions. You don't have to do anything in the actual body. It's just a list of config files. Okay. That is all from me. Questions, comments, concerns? I know that was a lot, but I hope it does provide a lot of context and a lot of, I guess, strategies to start implementing software, kind of thinking about hardware concerns and how that all kind of fits in, as well as kind of what the satellite actually does in its entirety, almost. Does anybody have any questions, comments, concerns? Yeah. Yeah. Would you want to know that there's a fault? If you're working on a system and you are 600 kilometers away, would you want to know that there's at least something wrong with your system? Yeah. Sure. Yeah. Yeah. 100%. Definitely. Do you want to make that change? No, that seems quite logical. Like, again, so like I do want to stress that like very few members of the team worked on this. So having all your brains, all your different perspectives contributing to this will only make it better. So yeah, I totally agree with that sentiment, and I think we should implement it. Yeah. See, yeah.
I know you talked a bit about the surviving, so I didn't see a graphic for it, but for example, there were two faults. One was a sun soak to be able to drop it. So if we have, for example, a low battery,
Yeah.
we have an over temperature.
Yes.
Is there an order in which they'll be processed, or if we're dealing with one fault and somehow another comes in? Yeah, we just thinking about that.
Yeah, I think every task, every fault will have a priority at a minimum, like a description priority and maybe like frequency of occurrence. Yeah. Yeah. Cool.
For the tasks you're talking about before, can you go back to your software sort of breakdown?
This one?
Yeah.
Yeah.
I think since we have multiple tasks competing potentially for the same resources, we need to have a priority sort of list for each task. Like if like one task has like needs to be executed over another, we shouldn't give them equal sort of opportunities to basically compete for each other. And
Yeah.
also, I think one of the sort of survival modes should be for memory, or not survival modes, but fault checks should be for memory. We could
Okay.
potentially have I don't know, maybe two separate storage places for memory, and then or three actually, and then if one doesn't like, it's very unlikely that like if we're checking frequently enough, it's very unlikely that more than, or like two out of the three will be wrong. And I think if one's wrong compared to the other two, we can basically say, hey, rewrite this memory pretty much. Or we can have like a checksum that if it doesn't, like we could have like two places with actual memory and one place that stores the checksum. And if the checksum doesn't match pretty much, we can basically just overwrite the non-working memory one.
So implement a memory check.
Yeah.
Or a memory fault.
Like potentially even we could store like a checksum if like even that if that's possible within like the OVC.
Okay.
And then basically we would have two like separate storage devices. And if one doesn't match the other, we can basically just overwrite it.
Okay. Yeah, that makes sense to me. Cool. Okay. I guess question, does anyone see anything else wrong with it? Because like, yeah, Steven.
On that library slide, the configuration or on some other sort of a permanent file storage, right?
Yeah, since we're doing multiple boards, I would say each board would have its own config file. Yeah.
I'm just thinking, because if those get tampered with while it's up, specifically off, it's easier for us to modify those while it's. How would we, perhaps we need to also build in some sort of a if. Yeah, no, there's essentially just ifs.
Yeah, I would say there's very little on like being concerned about bit flips. There's very little difference if you specify a pin number in a function rather than in a config file, because it's just going to get mapped to one another. It's just data. But from testability and usability point of view, having all your hardware specifications in one location is much easier for testing and development. Yeah.
Just imagine happening. Or just like one day you're uplinking and it's perfectly fine, next day you're uplinking. Why is this so slow?
Sure.
Right.
Sure. Okay. Cool. I guess that's all. Emma? Do you want to talk about it? My voice is a little sore.
Yeah, sure.
Harrison, we're gonna head out. But
Okay.
thank you very much for coming in.
No worries, I was happy to come.
All right, man. Take care.
All right, see you.
Peace.